This is lesson 6.3, Matrices for Linear Transformations. We're basically bridging now the work that we've been doing to really focusing on using matrices in linear transformations. So both this lesson and the next, we're just going to develop just a lot of the foundational elements that we need. And then in section 5, the last lesson of this chapter, we'll look specifically at how matrices are used to perform geometric transformations, things like reflections and rotations. So to start off, we're going to look at the two different ways that we've seen linear transformations expressed. And the first one in kind of this ordered pair format, vector format, and in two, more of the matrix format. Now, both of these are obviously completely legitimate and accurate ways to represent a transformation. But as I look at these, at least, I think that number two, writing this with a matrix has a number of benefits to it. One is I think it's actually easier to read. I don't know about you, but when I'm looking at number one, I'm having trouble kind of seeing where does one part of that break off with the comma and so on. In matrix form, it's again, I think easier to write. And if you're using any kind of software or calculator to perform these operations, also easier to do in matrix form. So again, not to take away from one, that first form, but I do think there are definitely advantages to having this in matrix form. And so that's partly why we are going to now, really for the rest of this course, for the rest of this chapter and chapter 7, really focus on linear transformations as matrices. So our first theorem talks about a standard matrix for a linear transformation. It says let T be a linear transformation mapping Rn to Rm, such that for the standard basis vector EI of Rn, and then we've got T of E1 equals a column vector, T of E2 equals a column vector, and so on. Then the M by N matrix whose n columns correspond to T of E sub I is A equals, and so you'll notice that basically all this is you've got T of E1 is the first column, T of E2 is the second column, and so on. So this matrix A is simply just kind of the mashing of all of these T of EI column matrices. And then it goes on to say that this is such that T of V equals A times V for every V in Rn. A is called the standard matrix for T. Okay. Probably doesn't make a lot of sense right now, but as we go through some examples and as we work through not only this lesson, but again, the next lesson as well, a lot of this will come together and I think make a lot more sense. So let's go ahead and just take a look at an example and just see what this looks like. So it says the standard matrix for the linear transformation T mapping R3 to R3 is defined by T of x, y, z equals x minus 2y plus 5z, tx plus 3z, and 4x plus y minus 2z. All right, so using the theorem then, basically what this is saying is that T of E, I'm going to start with not in matrix form, but basically because we're looking for the standard matrix here, we're looking for a transformation that in this case would map 1, 0, 0 onto the coefficients for x's, 1, 2, and 4. And then likewise, T of E2 is looking at for a transformation that would map 0, 1, 0 onto the y coefficients of negative 2, 0, and 1. And then T of E3 is looking at the transformation that maps T of 0, 0, 1 to the z coefficients 5, 3, negative 2. Okay. Now, again, we're doing this with matrices now, so rewriting these in matrix form, this basically looks like T of E1 is equal to the transformation of the column vector 1, 0, 0 equals 1, 2, 4, and so on. T of E2 equals T of 0, 1, 0 equals negative 2, 0, 1. And T of E3 is T of 0, 0, 1 equals 5, 3, negative 2. And again, based on our theorem above, putting together A, then T of E1 is the first column, T of E2 is the second column, T of E3 is the third column. So A, kind of running out of room here, A then is the vector 1, 2, 4, negative 2, 0, 1, and 5, 3, negative 2. Now, if you notice, if you look at the coefficients of the expressions in T above, right here, and look at your matrix entries, you'll notice that as I go across, I've got 1, negative 2, 5. That's the first row. I've got 2, 0, 3. That's the second row. And 4, 1, negative 2. That's the third row. So you're asking, wait a minute, isn't that just kind of like a coefficient matrix? Can I just take those coefficients and create the matrix A using that? And the answer is absolutely yes. It is really that simple. That's how we create A, is really just creating kind of that coefficient matrix using those coefficients of x, y, and z in this case. All right, so next definition is a composition. You might remember compositions from maybe some previous algebra courses, where a composition, if you remember, is like f of f, f of g, where you're taking one function and plugging it into another function. Same idea here. So when we talk about a composition of a transformation, here we've got T1 and T2. T1 mapping Rn to Rm. T2 then mapping from Rm to Rp is T of V equals T sub 2 of T sub 1 of V. So again, it's that idea that we're starting on the inside, right? We start with this T1 of V, and then we work that into T2. So it's kind of that inside out idea. And then here, V is a vector in Rn, and the composition is denoted by the following symbolism. So again, that little open circle, that just means composition. Okay. All right. And then just a little note that the domain of T is the domain of T1. The composition is undefined if the range of T1 does not lie within the domain of T2. All right, let's put together kind of a little map here to kind of see what's going on here. So basically what this is saying is we're going to start in a vector space. And in this case, it says it's mapping Rn to Rm. So this is going to be Rn. We're going to call this Rm. And we'll call this vector V. So vector V maps to some point, in this vector space by the transformation T1. Okay? Then, and we'll call this vector W, then this new vector W is mapped to yet another vector space by T2 and creates a vector, and we'll just call this vector U. And T2 is mapping from Rm to Rp, so this is Rp. All right. So that little note says the domain of T is the domain of T1. Okay, that makes sense. That's our first, that's Rn. That's the domain of T. Because T, remember, T is the composition of T1 and T2. So basically what this is really saying is that if I could map V directly to U bypassing that middle section, that would be the transformation T. Okay, so the domain of T, which is Rn, is also the domain of T1, which is Rn. Then it says the composition is undefined if the range of T1 does not lie within the domain of T2. Well, again, as I'm mapping V to Rm, this is the range of T1, right? These are the outputs from applying T1, but the range of T1 is also the domain of T2 because that's where we're drawing from as we map from Rm to Rp using T2. So the range of T1 has to lie within the domain of T2 or this doesn't work. So that's all that's kind of saying. All right, then we got a theorem out of this, and the theorem says that if T1 and T2 are linear transformations with standard matrices A1 and A2, then the composition T, defined by T of V equals T2 of T1 of V, is a linear transformation. Moreover, the standard matrix A for T is what we call the matrix product, or is given by the matrix product, I should say. A equals A2 times A1. So again, kind of going back to our picture, what this is saying then is that using matrices, we could take A1 and use that to map V to W. We could take A2 and use that to map W to U. And the matrix A, that standard matrix, is basically found by taking A2 times A1. Notice the order is kind of backward in that regard. It's starting with the second part and then multiplying by the first part. And that's going to be important. We'll see that a lot in the next lesson. All right, let's take a look at an example of this then. So this is saying let T1 and T2 be linear transformations from R3 into R3. And we've got the definitions for T1 and T2, the mapping definitions. Find the standard matrices for the compositions T, which is defined by T2 of T1, and T prime, which is basically in reverse T1 of T2. Okay, so just like we talked about in the previous example, A1, we can just write basically like a coefficient matrix. This is going to be 2, 0, 1, 0, 0, 0, and then 1, 0, 1. And this represents the standard matrix for T1. So this is the standard matrix for T1. And then A2, again, same idea. We're going to write the matrix 1, negative 1, 0, 0, 0, 1, and 0, 1, 0. And this is the standard matrix for T2. So standard matrix for T2. All right, we need to find T and T prime. T is the composition T2 of T1. And so in this case, to find T, we're really finding A, which is really finding A2 times A1. So if we multiply these two matrices together, and I'm not going to write that out, but obviously we're taking the matrices, multiplying them, we would get 2, 1, 0, 1, 0, 1, and looks like 0, 0, 0. So that is the standard matrix for T. Standard matrix for T. And then likewise, if we want to find T prime, that's the same as finding A prime, which is just reversing the order A1 times A2. So if we multiply the matrices in that order, we're going to get, looks like 2, negative 2, 1, 2, negative 2, 1, and then, 0, 0, 0, and then 1, 0, 0. And so that's the standard matrix for T prime. Standard matrix for T prime. Okay? All right. Moving on here. So inverse linear transformations. If T1 maps Rn to Rn and T2 maps Rn to Rn, if these are linear transformations such that for every V in Rn, so every vector in Rn, T2 of T1 of V equals V, and T1 of T2 of V equals V. So it doesn't matter which order we do this in, we get V. Then T2 is the inverse of T1, and T1 is said to be invertible. So basically all this is saying is obviously if I apply a composition and it takes me back to V, regardless of the order that I do this in, then it's an inverse. All right, and then we've got a theorem. Let T be the linear transformation mapping Rn to Rn with standard matrix A. Then the conditions listed below are equivalent. T is invertible. T is an isomorphism, which just means that it's one-to-one and onto. And the matrix A is invertible. And if T is invertible with standard matrix A, then the standard matrix for T inverse is A inverse. All right, so putting this together, kind of looking at this, we're going to take the linear transformation, mapping R3 to R3, defined again by the following. Show that T is invertible and find its inverse. Okay, So it says above, if T is invertible, it says right here, if T is invertible with standard matrix A, then the standard matrix for T inverse is A inverse. Okay. So what we're going to do is we're going to find A. So again, A is just going to be, in this case, 2, 3, 1, 3, 3, 1, and 2, 4, 1. And A inverse, which is literally just finding the inverse of A. So just use software, use your calculator, just find the inverse of A. That is -1, 1, 0, -1, 0, 1, and 6, -2, -3. And I'll leave it to you to verify that. But again, just use software to find that. So this is so A again is the standard matrix for T. And A inverse is the standard matrix for T inverse. Standard matrix for T inverse. And because A is invertible, right? Go back up to our theorem here. Because A is invertible, then it also means that T is invertible. All three of these are equivalent. So we know that because we were able to find an inverse of A, we also know then that T is invertible. So it's really all you have to do to show that is just literally, if you can find the inverse of the matrix, then you know that T is invertible. If you can't find an inverse, if it doesn't exist, then T is not invertible. Okay. Now, it says find the inverse then of T. So we're finding the inverse of T. So A inverse times X is just the matrix -1, 1, 0, -1, 0, 1, and 6, -2, -3. And then X just representing the variables x1, x2, x3. So this, if we multiply this out, is going to give us -x1 plus x2, -x1 plus x3, and 6x1 minus 2x2 minus 3x3. Which means then that just as T is written up here in this form, T inverse kind of writing it in that same form. Oops. Let's actually T inverse of x1, x2, x3 is just given by -x1 plus x2, -x1 plus x3, and 6x1 minus 2x squared minus 3x3. So that would be the inverse of T. All right, moving along here. Definition for the transformation matrix for non-standard bases. Okay. Let V and W be finite dimensional vector spaces with bases B and B prime respectively, where B is simply V1, V2 up to Vn, set of vectors, and T maps V to W is a linear transformation such that, okay, so it says T of V1 should be some parentheses in there. I'm missing some parentheses. Let me write those in. So you have a parenthesis there, there, and there. So then basically it says TV1 for B prime is the column matrix A11, A21, and so on. And obviously you can go along and see then that it follows that same pattern. And again, A is just those column vectors put together, those column matrices put together. Okay? All right. So it's kind of a similar idea here of what we've been doing, a little bit different, but it says let T map R2 to R2 be a linear transformation defined by T of x1, x2, given by x1 plus x2 and 2x1 minus x2. Find the matrix for T relative to the bases. And we've got the bases are defined as below. Okay, so remember that in B, it's just the set of vectors v1, v2, etc. In this case, obviously, just v1, v2. And I'm going to call the vectors in B1, or excuse me, B prime, W1 and W2. So T of V1 is just T of 1, 2, right? V1 is 1, 2. And using our definition here that we're given, if we just call this x1, x2, and plug those in, we will get 1 plus 2 is 3, and 2 minus 2 is 0, which relative to b prime is just 3w1 plus 0w2. And then t of v2, likewise, is t of negative 1, 1, which again, just plugging that into our definition for t, is going to give us 0, and negative 2 minus 1 is negative 3, which again, relative to b prime, is 0w1 minus 3w2. So then, t of v1 relative to b prime is going to be 3, 0, and t of v2 relative to b prime is going to be 0, negative 3. So then finally a is just, again, from our definition, a is just those column vectors joined together, those column matrices joined together. So 3, 0, and 0, negative 3. So that is our matrix for t relative to the bases. All right, so for our last example, we're going to continue kind of with this example from 4, and it says use for the linear transformation in 4, use matrix A, so use the matrix that we just found to find t of v where v equals 2, 1. Okay, so we know that B is the vector space 1, 2, negative 1, 1. So it's 1, 2, negative 1, 1. And from that, we can find V as a linear combination of these. So if I think of this as kind of C1, so it's kind of C1 times V1 plus C2 times V2, and I want to write 2, 1 as a linear combination, it'd be 1 times 2, 1, and then minus 1 times negative 1, 1. And you can find that by just setting up a matrix. You can just take the x1 from each of the vectors, so 1, negative 1, and then 2 from V. Second row would be 2, 1, 1. Use Gauss-Jordan elimination, and you'll find that C1 and C2 are 1 and negative 1. Okay. So that gives us V as a linear combination, which basically then we're going to use to start finding the transformations in relative to the bases. So from that, we're going to say that T of V relative to B prime is equal to the matrix A times V relative to B. And again, that's just coming from our definition up here. That's just this part right here. Okay. So A again is this matrix at the top here, 3, 0, 0, negative 3. And V relative to B is this right here, 1, negative 1. And if we multiply those matrices together, we will get 3 and 3. So 3, 3. All right, now, since B prime is the set of vectors 1, 0, 0, 1, so 1, 0, 0, 1, from that, we're going to say then, T of V is the linear combination of 3 times 1, 0 plus 3 times 0, 1, which is just going to be 3 plus 0 is 3, and 0 plus 3 is also 3. Okay? So that is our answer. That is T of V, right? Find T of V. That is our solution. Now we can check that because, again, remember back in example 4, we have a definition for T of V. So if I plug in 2, 1 into this, So if I let this be 2, let this be 1, let this be 2, let this be 1, I get 2 plus 1 is 3, 4 minus 1 is 3, we get the vector 3, 3. All right, so hopefully that makes sense. Like I said at the beginning of this lesson, we're going to kind of continue this into the next lesson. And so if there are some things that are still a little hazy, a little confusing, hopefully that'll get cleared up as you do some of the practice problems. But in the next lesson, we're going to go a little bit deeper with this, and I think there'll be even more clarity around some of the connections between some of these values and some of the things that we did in this lesson. So hang tight, and I will see you in the next lesson.